Hey Team Pecan, and welcome to today's lecture. In fact, the last lecture we're going to have for this semester. And today we're going to be talking about two topics that are near and dear to my heart: statistical thermodynamics and molecular dynamics. And what I love about today's lecture is that we're finally going to tie in some of the concepts that you learned in Chem 345, topics like internal energy, pressure, kind of macroscopic properties of a system, with our focus on Chem 346, which has been a lot on quantum states and energy levels. And so with that, let's go ahead and dive in with a little bit of recap on some of the lessons we've learned previously this semester. They're going to play a big role in understanding today's content. So to kick us off, something that we have explored in the couple of previous lectures is that all molecules have different types of motions and associated energies that are associated with the ways that they can move and interact with one another. We've talked about translational energy, we've talked about rotational energy, we've talked about vibrational energy, and last but not least, we've talked about electronic energies. And roughly speaking, a molecule's total energy is a sum of these different contributions. Not only that, but what the state of the system is going to be, or the state of the molecule, is going to depend on those different energy contributions and the quantum numbers that are associated with them. And so you may remember all the way back in Module 1, we talked about how translational motion can be studied or modeled using the particle in a box, and that those quantum numbers are n sub x, n sub y, and n sub z. We talked about more recently how rotational motion has the associated quantum numbers of j and m sub j. And we've talked also about how, according to the harmonic oscillator model, the quantum number associated with vibrations is nu, or sometimes called v. And once you take in total the different combinations of these quantum numbers that are available, that is going to be termed the microstate of the molecule, or the microstate of the system. And so what I've got towards the bottom of the screen is what one possible microstate might look like. And you can see that in order to determine the unique microstate, we have to pick different allowed values of all the different quantum numbers. And this seems pretty abstract, but I think a really good analogy is to say that the microstates of the system kind of work like a molecule's address. So, for instance, with Spelman College, in order to precisely locate where Spelman is in the landscape of the entire world, you might notice that we have different pieces of an address. We have to talk about Spelman's address number. We have to talk about the street that it's located on. We have to talk about the city and the state where it's located. And we have to talk about the zip code. And all of these pieces of information are needed so that we can uniquely identify where Spelman is located. We might call this Spelman College just microstate. And analogously, depending on what numbers or what letters you choose for the different quantum numbers, that is going to determine the molecule's microstate. The other big lesson that we learned, and that's going to be important for today's lecture, is that last lecture we talked about how the probability that a molecule will be present in a particular microstate depends on a couple of important quantities. One, it depends on temperature. And two, it depends on how the energies of the various microstates relate to one another. If there's a big gap between the ground state and the excited state, it's going to be relatively unlikely that we'll transition using thermal energy into that excited state. But if the states are close together in energy, we're going to see that it's very likely and very common to see transitions between ground and excited states. And so the two lessons that we learned and we concluded with last lecture is first, that if two microstates are degenerate, meaning they have different sets of quantum numbers, different addresses if you like, but the same total energy, those states are going to be equally probable to one another. And then the other lesson that we learned is that when we're comparing different energy levels, the relative probability that a molecule has a certain energy, E sub I, compared to some other energy it could have, E sub j, is given by this Boltzmann distribution. And you may remember that in terms of the variables, these letters G relate to what are called the degeneracy factors. K sub B is our Boltzmann constant, and T is the temperature in Kelvin for the system. Okay, so now we've done a little bit of that review. Let's talk about what we're going to learn in today's lecture. And I say we're going to have two focuses for today. The first is that we want to understand what the Boltzmann distribution and these equations we described above have to say about the overall properties of a system. In other words, if we're studying not just one, but many molecules, say studying water as a liquid instead of water as a gas, how could we use the Boltzmann distribution to understand overall properties of that system, like water's density, its pressure, its temperature, what its energy looks like, what phase it wants to be in? And one phrase that we're going to learn in today's lecture is going to be something called the partition function. And so one of my main goals for today is to introduce us to this partition function and describe a little bit how it can be used. The second big topic for today's lecture is going to be how we can practically apply statistical thermodynamics to study complex systems. Again, going back to that liquid water example, there's lots of things we might like to know about water, or maybe even a protein in water. And the partition function is going to take us a long ways, but it's only going to take us so far. And so the second big topic that we're going to talk about today is something called molecular dynamics. And with that, let's go ahead and get started with our first topic for the day. So this is something that is very related to the Boltzmann distribution that we talked about last lecture, is essentially just a different way of phrasing it. Instead of considering relative probabilities comparing two states to one another, we might be interested in knowing instead, hey, what's the actual probability that we might see a molecule be at a particular energy level? And it turns out there is a really good equation for studying that. And the equation reads that the probability, little p sub I, of being at a certain energy level I is equal to that Boltzmann factor, so that's g sub I, the degeneracy factor, times e to the negative beta times the energy state. And you might notice that compared to last lecture, where I kept describing things in terms of kb times T, where kb is Boltzmann's constant, T is the temperature. Because that factor 1 over kBT gets used so commonly, a lot of folks have taken to abbreviating that with its own special variable called beta. So we can say that the probability is equal to the Boltzmann factor in the numerator divided by something called Q. And I'm going to describe what Q means to you both mathematically and in words. Mathematically, Q is equal to the sum of J, where J is going to go over all of the allowed values of the energy. And within J, we're going to sum up the degeneracy factor times that Boltzmann factor one more time. So you can see that Q and then what happens in the numerator are really related to each other. The only difference is that in the numerator, we're only considering one energy level, and in the denominator, we're summing over all possible energy levels. In words, this term that I put in the denominator, where I'm using the letter Q to describe that, is something called the partition function. And the partition function is really interesting in that qualitatively, it represents the number of microstates that are thermally accessible to a system. And so I've got a short graphic here which depicts an energy level diagram really 4 different times. That same energy level diagram, but it's showing us what is the difference between the number of states that are populated at low temperature on the left versus the number of states that are populated at high temperature on the right. And there's a couple different things that I want us to notice. The first thing I want us to notice is that at low temperature, Q is very close to 1. And what this means is that here, where there's only one ground state, it's singly degenerate in this kind of ladder of energy to states that I'm depicting, here, only one energy state is what's termed thermally accessible, meaning that I only have enough thermal energy to be in the ground state, and it's very rare. You can kind of see with these histogram bars that are shooting out horizontally that every once in a while the molecule is allowed to make it into the excited state, which is why Q is just a little bit bigger than 1, but by and large we're only in the ground state. If we contrast that with what's happening at high temperatures, you may notice that at high temperatures here multiple states are thermally accessible. And so you can see that there is kind of a broad distribution at high temperatures of which states are being populated by a little bit, but Q is sort of taking a weighted average of that and saying, hey, the first 4 states are very easily accessible. Going on up from there, we're going to see decreasing amounts of population in those states. And so Q qualitatively represents the number of microstates that are thermally accessible to the system. And I think it's useful to walk through a little bit what the math looks like when we're studying the partition function and we're trying to apply it to a particular system. So let me show you an example of what this partition function looks like mathematically in the exact expression for Q if we're considering the ladder of energy states like in the figure that I've shown above. And just for reference, I'm going to say that this is an equally spaced ladder, and I'm going to set my ground state energy to 0 for kind of ease of what the math is going to look like, which means that our first ladder rung is going to have an energy of E equals 0. Our second spot on the rung is going to have an energy of epsilon. And since these rungs are equally spaced, that means our rungs are going to have energies of 2 epsilon, then 3 epsilon, etc. Okay. And so remember, our expression for Q is that Q needs to be the sum over all available energy states, taking into account their degeneracy factors. But since it's a ladder of states, which I'm saying are all singly degenerate, that means that G sub I is going to be equal to 1 in all cases. So the only thing that we need to do, and what I'm showing in the second line, is that we're going to take our energy for the 0th level, and because the energy is equal to 0 in this case, e to the negative beta epsilon sub I just becomes e to the 0, which later you're going to say I'm going to simplify to 1. That means that the energy, or that Boltzmann factor for the first excited state, is e to the negative epsilon beta times epsilon. The second energy level is going to be e to the negative beta times 2 epsilon, etc., etc. And in the third line, what I'm showing is just a little bit of algebraic simplification. And you'll notice that based on how exponents work, I can express these higher order terms as e to the negative beta times epsilon squared, then cubed, then to the 4th power, etc. And that doesn't really look like I've done a whole lot of useful work, except that there's a trick you may have learned in your high school calculus class, which says that there's a series expansion, where if you ever notice a trend where you're summing up over 1 plus something x plus x squared, etc., that simplifies really nicely. It's actually just going to be 1 divided by 1 minus whatever the term that's repeated is. And so for our purposes, the repeated term is e to the negative beta times epsilon. And so our expression for capital Q is ultimately going to simplify to 1 divided by 1 minus beta times epsilon. That's kind of cute. It looks like the partition function was going to be really complicated, but it simplifies nicely. And in terms of expressing these probabilities, now what we can say is that the probability of being in a particular energy level is equal to that Boltzmann factor in the numerator divided by Q. And because our states are singly degenerate, G sub I is equal to 1, so we can ignore that in the expression, and we ultimately get that the probability is equal to e to the negative beta times epsilon sub I, so the energy of a particular state, times 1 minus e to the negative beta times epsilon. Something that I think is really useful to do now that we have this expression is to try and chemically interpret it. And so what I've done is I've used Desmos to plot a table of what these different energy states look like and their associated probabilities. So each of these data points that you're seeing in Desmos represents both what the energy level is. So here you can see my E equals 0 state versus my first energy level, my second energy level, and so on and so forth. And you can see what the probability is of observing it in that state. And I want us to notice a couple things to bring us back to our original, all the way back to lecture 1. is that first and foremost, if you add up all of these energy states, you're going to have the probability sum up to 1. That is our chemically intuitive result of whatever all our possibilities are, the probability of that possibility occurring, all those have to sum up to 1. So we see that happening in this case, where 0.77 plus 0.173, et cetera, that's going to add up to 1 if we add up all the states. The other thing that I want us to see is that we can now see more directly than we did last lecture what is the probability of being in a particular state. And at the temperature that I've plugged into the expression at this particular moment, it looks like there's a 78% chance of being in the ground state, maybe an 18% chance of being in the first excited state, and then it gets less and less probable as we go to these higher energy states. Remember that beta is equal to 1 over kBT, meaning that it's inversely proportional to temperature. So something that I can do is I can increase beta, which simulates the result of decreasing the temperature. And watch what happens to our expression when we do exactly that. Hopefully you can see that at low temperatures, when beta is relatively big, that only the ground state is populated. In fact, at this particular value of beta, there's a 99% chance that we're found in the ground state and very small probabilities that we're in one of these excited states. Conversely, if I start to make beta really small, these probabilities start to average out. And in fact, if I draw a line through them, you can see that at very small values of beta, which again, since beta is inversely proportional to temperature, correspond to high temperatures, we get nearly equal probabilities of being in any of those states. And so hopefully that collaborates with what we learned last lecture, which is that at very high temperatures, there's really no meaningful difference between the energy levels, and they look from far away as if they're almost degenerate with one another, meaning that there's going to be equal probabilities of being in the different states. And so again, what we can see now that we've talked a little bit about the partition function and calculated that so that we can calculate these exact probabilities for being in a different state, is that the probabilities add up to 1, and that the relative probabilities match the intuition we learned last lecture, which is that at low temperature, it's much more likely for the ground state to be occupied, and at high temperatures, these probabilities sort of flatten out, and there's equal likelihood of being in any of the available states. And at room temperature, of course, the situation is somewhere in between, where it's more likely to be present in the ground state, but we do see some of the molecules being present in one or more of the excited states. Okay, so we talked a little bit about this partition function, and I do want to note before we move on that different systems are going to have different expressions for Q, and hence different expressions for what these probabilities look like. So this expression that I've boxed applies to this ladder of energy states, which looks like the harmonic oscillator. It's not going to apply exactly as is to a rotational energy landscape or electronic energy landscape, but that's okay. And then the second thing, I think the more important thing to point out, is that I've chosen an example where the math isn't too bad, but for complex systems, the expression for Q can get really lengthy. And we're going to see at the end of today's lecture that in fact for complex systems, we're going to have to revert to calculating Q numerically or doing some sort of simulation rather than trying to analytically explore what Q should look like. Before we get to that though, I want to talk a little bit about why, besides the example that I just gave, why we would want to calculate Q in the first place. As it turns out that once we know the partition function, that's going to give us knowledge of any thermodynamic quantity that we're interested in. So some of the variables that you talked about in Chem 345, like U, the internal energy, S, the entropy, G, the Gibbs free energy, all of those can be calculated and really derived from the partition function. In the space of this lecture, I'm not going to have time to go over each one of these different quantities of interest, but I'm at least going to highlight for us how the partition function helps us understand the total energy, U, of the system. So, just like we learned in lecture 1, the expectation value, so the average value of something like the internal energy, is going to depend on the probabilities and the quantity that we're interested in. So here, I've got for us this average expectation value formula, and this is something that we presented directly in lecture 1. So if it's a little bit unfamiliar, I encourage you to go back and review that lecture a little bit, but otherwise, hopefully we can remember that the two things we need to know in order to calculate an overall property is those probabilities and the quantity that we're interested in. And the good news for us is we just derived a way to calculate those individual probabilities, and we determined that those probabilities were equal to our Boltzmann factor, g sub I times e to the negative beta times epsilon I divided by q, the partition function. So that's our p of I piece. And then to the right, the quantity that we're interested in is what's the energy. So we're going to multiply to get the average energy per particle times E sub I. And how this is related to the total energy of the system is that if the expression I've just given you is the average energy per particle, then we simply need to multiply by n, the number of particles, in order to get the total energy of the system. And so let's do one example with what this total energy would look like. And here I'm going to choose an even slightly simpler example than what we did in the first example. I'm now going to consider just a two-state system where the energy of the ground state is equal to 0, and the energy of the first excited state, and really only excited state, is equal to epsilon. So if you like, you can think about this as being sort of like the harmonic oscillator, but here we're only considering what might happen in the ground state and the first excited state, rather than considering these overtones or these additional excited states. So to calculate Q, remember, we need to sum over each of the different allowed energy states, taking into account their degeneracies. Both these states are singly degenerate, and we've only got two states. So our expression for Q is going to end up being equal to 1 plus e to the negative beta times epsilon. The internal energy is then related to Q, that partition function we just calculated, but we also have to worry about summing over each of the different individual energy levels and taking into account the energy states and that Boltzmann factor, e to the negative beta times epsilon. And so if we do that, notice that our first energy state, if we plug in this expression for our first energy level, well, e sub epsilon sub I is equal to 0, so this whole term is going to be equal to 0. And as for the first excited state, well, we know that the energy is equal to epsilon, and the Boltzmann factor is going to be equal to e to the negative beta times epsilon. Plugging in our value for Q, that is going to then give us that the total energy of the system is equal to capital N times epsilon times e to the negative beta times epsilon divided by 1 plus e to the negative beta times epsilon. And I think it's best for us to view this answer graphically rather than focusing too much on the equation, but I want us to notice a couple different things. First thing I want us to notice is that both of these graphs are saying the same information. You'll just notice that the top graph is a zoomed in version of the bottom graph. So both of these are showing us, as a function of temperature, how is the energy of the system changing. And one thing I want us to notice is that at small values of temperature, so as the temperature approaches 0 Kelvin, so does the total energy of the system. And that should make sense to us because all the molecules at low temperature are going to be in their ground state. And so the total energy of the system is just the sum of all the individual energies. And since they're all in their ground state, each molecule is going to have an energy of 0. And so the sum of that is also going to equal 0. We can also explore the opposite limit. What happens as the temperature grows increasingly large? And you may notice that on this graph, it's approaching an asymptote of 0.5. What that tells us is that as the temperature gets really big, the internal energy starts to look like 1/2 n times epsilon. And hopefully this also feels intuitive to us, because if on our energy level diagram, half of the molecules have an energy of 0, and the other half of the molecules have an energy of epsilon. Remember, the reason that we expect there to be a half-half split is that at high temperature, both of these states are going to be equally likely to be populated. That tells us that if we have n molecules, on average, half of them are going to have an energy of 0, half of them are going to have an energy of epsilon, which means that on average, each molecule would have an energy of 1/2 epsilon. And that gives us exactly what we see on the graph. And so again, what's really nice is that even though we might have been able to predict what the energy and what the total energy should look like in these extreme cases of either 0 Kelvin or at really high temperatures, we can use this expression for the total energy to predict also at room temperature or cold but not too cold of temperatures. What would the total energy of the system look like? And so I hope I've shown you in these two examples that there's a lot of value in being able to calculate the partition function because it's going to tell us information about all these thermodynamic quantities that we were interested in back in the previous semester in Chem 345. However, I'm going to have to give us a caveat that for more complex systems, all of a sudden the number of microstates starts to balloon. You can imagine that if I have one molecule that has a set of quantum numbers, and then it's next to another molecule who has its own set of quantum numbers, all of a sudden the number of microsystems is going to be really too large to handle. And similarly, especially analytically, sometimes it can be hard to come up with an easy to manage expression for Q. Sometimes it can even be impossible to come up with an analytical expression for Q. And so we don't want to be stuck as scientists. We instead want to be able to pull out another tool in our toolkit for exploring these thermal energies. And the tool that I'm going to wrap up today's lecture with is talking about something called molecular dynamics. And so molecular dynamics is a process of, instead of enumerating all the microstates, calculating their energies, calculating their probabilities, adding them up, to actually just sample the different microstates. It's kind of in the same way that when, as the United States, we go to vote, it takes a lot of work to get the full vote tally to really determine who's going to be president next, who's going to be our next senator. But it's much easier to sample a small but representative part of the population via polls to get a sense of what the election result is going to be. So if calculating the partition function is like doing the full election, molecular dynamics is like doing polls, sampling a representative part of the population in order to get a very good estimate of that same information. So the big idea of molecular dynamics is that we're going to sample over a reasonable number of microstates, focusing on the ones that are thermally accessible at whatever temperature we're interested in order to get very good estimates of a system's properties. And so the input to a molecular dynamics simulation is actually something that you're already familiar with from one of our previous lab experiments. If we go on to something like ChemCompute, which is one website that you can use to run these molecular dynamics simulations, what you're going to see is that we have to give ChemCompute a little bit of input before we can run our molecular dynamics simulation. This first part, what we have to study is we have to give some information about what type of system we're simulating. And on ChemCompute, there's lots of different options. The screenshot that I'm showing is if we wanted to just simulate water by itself, but there's options on ChemCompute to add in salt ions, to add in proteins, to add in small molecules. And so there's lots of different options on what you can simulate. A next big decision, what I've highlighted in green, is that we have to decide how big of a system to simulate. And you probably noticed in lab there's some trade-offs where the bigger we make our box size, the more representative it is of what an overall liquid would look like. However, bigger box sizes translate to longer simulation times. And so the bigger you make your box size, the longer you're going to have to spend waiting to get your results. There's a couple other options we have to choose in ChemCompute. Like I've shown in blue, you can choose whether you want to run your simulation of something in the gas phase versus if you want to run it in a solvent. So far, ChemCompute only has water as a solvent, but in these more sophisticated software packages that you could use, there's lots of different solvent options that you can choose. You have to choose, like I've shown in pink, sort of what experimental conditions you might want to run. You may remember all the way back in general chemistry that we talked about systems that were under constant volume conditions. That might be like a bomb calorimeter versus things that are constant pressure conditions. That's more ambient atmospheric pressures like we're used to. Most of our lives, by the way, are lived under constant pressure conditions. And so you can see that we either choose the simulation to be what's called NVT, meaning we keep the number of molecules, the volume, and the temperature constant, or we run things at NPT, meaning that we keep the number of particles, the pressure, and the temperature of the system constant. And then last but not least, we also, of these experimental conditions, have to choose what temperature we want to run. And that can just depend on the context that you're working in, what an appropriate choice of the temperature would look like. The other options that we have to choose relate to how long we want the simulation to run and where we want to sort of take our poll data. Once we start the simulation, we might, just because the computer is going to generate an initial configuration of the molecules, we might accidentally start in kind of an awkward configuration. Maybe for water, our hydrogens are pointed towards each other instead of forming nice hydrogen bonding networks. Maybe the water molecules are packed a little too closely together. And so there's no guarantee that your initial configuration is going to be a very good representative poll, if you like, of what this system is going to look like under equilibrium conditions. So often you run a first set of steps in your simulation that are called minimization steps or equilibration steps. This is the part of the simulation where we're going to ignore that data. We're going to discard it entirely, but it is necessary so that we give the system some time to relax, to generate what looks more like equilibrium configurations so that we can be ready to take data that looks like so-called good poll data. Once we've done enough equilibration, the next part of our simulation is going to be what's called the dynamics part of our simulation. And that's kind of where this term molecular dynamics comes from. It's because we're going to let the simulation take place, and we're going to watch all of the molecules in our system move and wiggle and jiggle over time. This dynamic step is the amount of time we're going to use in order to record statistical information about the system. If you like, this is going to be our representative sample that we take poll data on. And then last but not least, we're going to have to choose how frequently to have our time step. If you like, a short time step corresponds to really watching each moment in time very carefully, and choosing a bigger time step is almost like you're watching a YouTube video at 2x speed or 1.5x speed. Hopefully, if you're watching this video, you're probably watching it more at 1x speed so that you can get in all the good details. But the bigger the time step we choose, the faster the simulation is going to take place, the longer we can watch these molecules move in time without having to take too much data or spend too much computational time on it. However, I'll warn you that if we choose too big of a time step, our movie is going to get choppy. And in fact, you can often run into numerical stability issues. And so I would recommend for most systems that we choose something, time steps that are typical are somewhere between 0.5 and 2 femtoseconds. Once we hit go on our simulation, we let ChemCompute spend some time generating an output. I want to walk through two different things that this output is going to give us. The first piece of output that we're going to get is a kind of graphical view. And I've chosen a different screenshot than what's shown in ChemCompute just because this was a really nice simulation that some other researchers ran that shows the transition of water from being ice. You can see in the top right-hand corner, it has this nice lattice structure. It corresponds to solid water, to what water looks like when it goes into the liquid phase. And so one of the outputs that you get from a molecular dynamics simulation is simply a visualization and a movie of what's happening to these water molecules over time. And these can be really useful for visualizing motion, for watching what sorts of fluctuations take place in the molecules, how they're moving around. You can directly observe any phase transitions that might be happening, and really a ton more stuff. The second type of output that you get from a molecular dynamics simulation is a bunch of data that you can plot. And so I've shown on this screenshot how you can see what the density of water looks like over time, but there's lots of different options on ChemCompute. And if I switch over briefly to my output window, you might be able to see that we're able to study what the internal energy looks like, what the pressure of the system looks like, and you might also be able to look at the individual terms. For instance, if I wanted to understand what of the energy of the system is subdivided into potential energy versus, say, kinetic energy. But if we focus back on this plot of density versus time, I want us to notice two things. First, there's a region in our simulation where even though I chose a certain time for the simulation to equilibrate, it looks like I should have chosen a time that was slightly longer. Because you'll notice that a lot of these, my density of water is rapidly changing for the first little bit of the simulation. And that's not really ideal. It's not what we want. And so oftentimes we discard the first part of our data, especially if it looks like the data, instead of fluctuating around some constant value, is rapidly changing. Once our simulation data has sort of averaged out, then that's going to tell us that the properties of interest, let's say if I'm interested in understanding what the density of water would be predicted to be at a certain temperature, those properties of interest can be determined by taking an average of all of our data once we've reached some sort of equilibrium time. And so you might notice from this data that at the temperature I ran the simulation, which was 298 Kelvin, so very close to room temperature, that I'm predicting the water in the simulation to be a density of 1.03 grams per milliliter. Should be the units on this. And so hopefully that comes across as really neat, because we haven't done any experiments, and yet we're able to directly simulate what water is going to do under reasonable conditions. But I want to leave us with a couple of important considerations and caveats to note if you ever wind up running some MD simulations yourself, or what might be really likely, hearing about them in some sort of research talk. The first thing I want to point out is that molecular dynamics simulations are only as accurate as the model's method for determining or approximating what the energies of the system look like. That mathematical model is termed a force field, and I can say, since this is my research area, that these models are constantly improving. We've gotten so much better over the last couple of decades, but they're still approximate enough that we have to treat them with caution and validate them against experiment whenever possible. If you've been paying attention, you might have in your mind that the density of room temperature water is 1.00 grams per milliliter. And so you'll notice that we have a little bit of an error here in terms of what our prediction is for the density of water using this very approximate force field versus what we expect from experiment. And so MD simulations, depending on the force field, they can tell us a lot, but they're only so accurate at predicting what real experiment is going to look like. The second thing I want you to note, and you've already seen this in your laboratory setting, is that there's always a trade-off between accuracy and speed. If we run longer simulations or shorten our time step or run the equilibration period for longer, those are all going to help our simulations be more accurate and more robust, but it's going to increase the computational cost. And so a wise scientist is going to have to make choices about where to prioritize accuracy versus where to prioritize speed. And the third and final thing that I want us to point out, and that you're going to be able to read a little bit about using the article that's posted on Canvas, is that molecular dynamics simulation are being used all over the place at this point. And so the applications are really far-reaching. It gets used all the time these days in drug discovery processes. It gets used in the design of new materials. And like you've seen in the lab, it's something that can give us a lot of chemical or mechanistic insight into chemical reactions or non-covalent, different types of interactions that are happening between molecules. It's been able to study what does a protein look like when it folds. And so there's really just a lot of neat things that you can do by studying molecules using these MD simulations. Okay, so that's all that I've got for us today. I want to give us, before we wrap up today's lecture, a few takeaways to really focus on. what are the most important points that I wanted you to learn today? The first takeaway is hopefully this is a reinforcement from last lecture, but we've seen that the macroscopic properties of a system, its internal energy, its density, its pressure, all of those things depend on two quantities. One, the temperature of the system really matters, and two, the energy of the individual microstates also really matters. A second takeaway from today is that all of the information that you need on a system is contained within Q, its partition function. And so this is a topic that we've really only skimmed the surface of in today's lecture, but hopefully you are able to see that if we know Q, the partition function, we can calculate the probability of being in a given energy level. We can calculate the total internal energy. And in fact, if we explored farther, you'd be able to see that really any thermodynamic quantity that we're interested in is something you can know through the partition function. And then our third and final takeaway for today is that for complex systems where the partition function is difficult or maybe even impossible to solve, we can instead take a different approach and use molecular dynamics to explore both macroscopic properties of a system as well as get a microscopic view into what these molecular motions look like. And with that, that is all that we've got for today. I look forward to seeing you all in class.